Hi, everybody. Have you ever thought how Google exactly knows what you're looking for, even when you don't type your question completely? Or how hospitals can predict the patient's risk just by scanning through thousands of doctors' notes? Or Netflix figures out the mood of the movie just based on the description? The secret behind this is text mining. Text is being mined. This is an art of turning messy, unstructured text into valuable insights. In today's video, we're going to decode what text mining really is, how it works, why it's one of the most powerful tools connecting language, business, and data. ChatGPT and Gemini really use text mining. We're going to learn the difference between structured and unstructured data, or how to convert unstructured into structured data. We will convert the text into numbers. We will understand what does TF-IDF and TF-IDF really means. What's tokenization? What's text cleaning? You must have heard of data cleaning. We're going to learn text cleaning here. There are three ways to clean the text. One is stemming and lemmatization. We can use stop words and spelling corrections. We can use another technique called part of speech tagging. We can reduce the dimensions with a singular value decomposition or SVD. Whose dimension are we reducing? We are reducing the dimension of the matrix. When we converted the text into structured data set, it becomes a matrix, and now we are interested in reducing the size of that matrix because text means a lot of words. That means a huge matrix for machine learning algorithms to work on. And this way, we reduce using singular value decomposition, we reduce the size of that matrix. Once the size is reduced, we apply machine learning to the text. It's the basic, simple machine learning that we used before. We can either use regression, we can use classification, or we can use unstructured learning called clustering. The challenge is data labeling. How do we label that data which is unstructured, non-classified, which does not have a target variable? We will look at a real-world example of VA hospital fall detection project. Like we have a big data set and we don't know whether those patients who have come to VA have come for the reason that they fell down. And we're going to learn from the data whether this person or the new person whom we are really interested to know has really come for a fall related reason to VA hospital. We will summarize all the learnings from all of this and we'll look at the key takeaways. But first, let's talk about the use case of why we are even interested in text mining or why we are interested in learning about text mining. Think of text mining as building the roads on which ChatGPT can drive its car. NLP, or natural language processing, serves the traffic rules on the roadway, and ChatGPT works like a self-driving car that has mastered them all. It does not need to be consciously thinking about all these stop signs anymore, but it cannot drive without that foundation of knowing about the road, knowing about those traffic rules, which it has already learned. So these traffic rules pertain to text mining. Sorry, traffic rules pertain to the actual roadway. I'm sorry. So this roadway in this example is the text mining road, and the traffic rule represents the natural language processing that serves another layer of foundation. On top of it sits the ChatGPT learning algorithm that works on deep learning. So it's an amalgamation of multiple layers, which has now, over a period of time, has been built into the ChatGPT algorithm. And even if you go try to learn your own data set using Gemini, ChatGPT, it will tell you the cost of learning or tokenizing the data set that you have provided to learn it. We're going to learn what tokenizing really means. So let me read this out for you. Text mining is data preparation layer. Before any model like ChatGPT is trained, enormous amount of raw data from books, article codes, websites, etc. needs to be cleaned, filtered, and structured. This process uses text mining techniques, including first, we just mentioned tokenization, stop word removal, normalization, and deduplication. You're going to learn in this video what all this really means. Tokenization simply means splitting the word or text or sentences or booklets into different texts or words or subwords. We will remove uh, we will remove the stop words we will decide on which words really carry the meaning. If the words are very similar, we will just replace them with a single word. We will handle punctuations in the normalization step. We will handle the punctuation, capitalization, and special symbols in a slightly different or nuanced way. And we will make sure if the words are repeated or they are not serving any purpose, we remove them in the step of deduplication. Natural language processing is another layer that ChatGPT has mastered. It's the conceptual and algorithmic layer. It works on tasks like uh, part of speech tagging, name identity recognition, syntax parsing, lemmatization, and sentiment detection. In this video, we are more interested in the text mining. NLP we will cover in the next video. So the use case, just to differentiate between all three, text mining is one of the basic or foundation layers that ChatGPT or Gemini or any other model for that matter will work on. The purpose is to clean and structure the raw data or raw text. It's still in use and it creates tokenization, removes duplicated words. Next is traditional natural language processing. The purpose is linguistic and learn from the information. What text mining does not do, it does not it does not learn from the data. It does not understand that data. It simply creates a structured data from unstructured data and tries to make sense out of it using very basic mathematical algorithms. For example, what's the frequency of word text in a text mining essay? So it will tell you this text in a text mining essay has come 150 times. It will tell you a combination of words has come so many times. It could eliminate a combination of words by a single word, replace a combination of word by a single word. That's again part of text mining. So we create a structured data set. We make the whole text simple enough for the model. It's like regression model, classification, or unstructured learning models, unsupervised learning models to learn from the unstructured data set. Then what Gemini and ChatGPT have really mastered. So these two are pretty common. Text mining and traditional NLP, their algorithms are freely available. It's pretty easy to use. But what these softwares or these models have really mastered is the transformers. They really create some deep learning and they generate the data or generate the text out of the learnings they do. They form the core engine of the data set, and that's the real thing that ChatGPT, GPT-4, GPT-5, Gemini, Grok, uh, Claude, they all use as their core engine. That's the transformers. All right. So we're going to learn about what is text mining, what's structured versus unstructured data, how to create the term-by-term document metrics, and what's singular value decomposition, supervised versus unsupervised, and we're going to go over an example project in this video. Let's start with a common misconception. When we say text mining, we don't really mean Alexa or Siri listening to your voice. That's speech recognition. Text mining does not understand the meaning of the words the way humans do. It finds patterns in text using statistics. It finds patterns in text using statistics. It does not care if the word is happy or sad. It only cares how frequently it appears and how those patterns differ from one document to another document. So what's text mining and what it is not? It's not Alexa, it's not Google Assistant, it's not dictation, it's not speech detection. It's simply learning the patterns from the text using statistics. It does not care about the words and phrases, it only cares about the frequency of the words. All right. So, what's the use of this text mining? We're going to learn that. Think about how much text we generate every day. We generate emails, we look at reviews, we look at tweets, we look at news articles, research papers, medical notes, and so on and so forth. In business, text is a gold mine, but it's all unstructured. It's all spread unstructured. By that I mean it's in the form of an essay, not in the form of tables, which have columns and rows and a target variable. So from essay kind of text to organized tabular form of text, That's what we are trying to achieve. Text mining helps us to transform the chaos of something into a measurable insight. Example, how hospitals detect the health risk of based on the physician notes. Physician always notes what kind of uh, patient has been observed to or what's the diagnosis. But if you look at the hospital level, they want to read all those notes and detect what kind of risk are we really looking at in broader in general terms in this hospital. Companies can gauge public sentiment from social media. News agencies can group related stories automatically. So text mining is all about extracting the structure from the unstructured data. So can we take advantage of text and find patterns in it? I believe yes, but there are two challenges. What kind of patterns are we really talking about? We got to first define that. And what machine learning requires is structured data. We don't have the structured data yet. We're going to learn how we achieve that. Text is unstructured as I just described it. For example, there is tech news. There are pages after pages, documents after documents, based on some key terms like processors, memory, storage, cloud, internet. Once the text mining scans through all these texts, it finds out processor has been repeated 50 times in 50 documents. Memory 100 times in 50 documents. Storage 200 times in 50 documents. Cloud 100 times in 50 documents. Internet just about 1,000 times in 50 documents. That's how it will conclude. Oh, this is a group of document that pertains to tech news. Similarly, it can differentiate between the tech news and the health news because it now knows that blood pressure has been repeated 1,000 times in 50 documents, and cholesterol has been talked about in 100 documents, 100 times in 50 documents, and cold and flu 50 times in 50 documents, something like that. So now it knows it's a cluster. Even if you don't have a target variable, it runs like unsupervised learning models and differentiate between this kind of document and that kind of documents. So these are now so we are going from unstructured, totally unstructured, to some level of structure, some level of groupings in the documents or text or rows. Here we look at structured data set. For example, there's a customer ID, age, homeowner one, and his income is $100,000. Second, we got the age, we got the homeowner, whether he's the homeowner or not, and we got his income. So that's kind of an example of structured data set. But when we talk about unstructured, that's what we are right now interested in. It's like we got the ID or the document number, like page number, and we got a lot of text, like 100 lines of text here, 100 lines of text there, and so on and so forth. So that's what I really mean by unstructured data set. And this was a structured data set. So from unstructured to structured, how can you make this data, these pages uh, into a structured data set, which is in the form of rows and columns? So we convert the unstructured to structured first, for example, in a binary way. It's like term by term document metrics. So pediatrician. So we separate out all these words and make them into column. Pediatrician should carefully evaluate kids. So all these are now columns. Now you got 10 columns, or let's say there were 100 columns. So 100 columns, if there were 100 sentences or 100 words, we now have 100 columns. What it's doing is every time this word, which has a column, appears, for example, should comes in the second document or second page. So at should, it gives you a binary yes, yeah, should appeared in this sentence. And pediatrician did not appear, carefully did not appear. And as we go on, it kind of frames a sentence in the form of binary zeros and ones. So first page is now in the form of zeros and ones because pediatrician appears one, should appears one time, carefully appears one time. So it uses the first row as the first way to determine what kind of columns it needs. Challenge is it makes the metric so much huge because you got hundreds, thousands of words and there are different combinations, and this is pretty consuming. But it's one of the ways. It's called term by term document metrics. Different types of term document metrics. We just looked at the binary. Now we can also do like a count of the term. So example, we have a count metrics. In this one, for example, pediatrician appears, example, 9 times. Here we are only capturing, in the count metrics, we are only capturing how many times pediatrician appears in that sentence or on that page. for that matter. Should appeared 6 times, carefully appeared 1 time. In the next sentence or next page, pediatrician did not appear at all. Should appeared 13 times, carefully appeared 0 times. There could be another kind of metrics, that's the term frequency. What we're trying to achieve is kind of normalize this. So count of term by document term frequency. So we are essentially normalizing that so that we are easily able to process this data. The count within a document. What we are trying to achieve here is, if there are 100 words in this document, so we divide each of these terms by 100. So 100, 100. So that makes it 0.09 here, 0.06 here, and 0.01 here. So, for example, here the term frequency is actually the inverse of document frequency. Now let's understand what we really mean, and let's look at with the help of an example. Term frequency, which is the inverse of document frequency. So term frequency represents TF, IDF means inverse of document frequency. So term frequency, so how many times a term appeared in that document or on that page, times the inverse of document frequency. Where IDF is, how do we get the IDF, inverse of document frequency? We got a formula for that. Log of total number of documents, total number of documents with this term in it. So if we got 100 documents or 100 pages in a Microsoft Word file, for example, 100 pages, and on each, and if we are interested on, we are talking about page 1 right now, total number of documents is 100, total number of document with this term in it. For example, this term should, so we are interested in this word or term called should, and if it appears, total number of documents with this term. So we have, out of these pages, we have should on almost every page. So we divide these two numbers on 100 pages. So 100 is the number of pages. So 100 over 100 gives me 1, and I do like a log of 1, and that gives me the inverse of document frequency. Example, TF represents term frequency, IDF inverse document frequency. So TF and IDF example, we are looking at 100 terms in this total, of this document. Prediction, we are interested in this word, appears 5 times in just this document, just this document, not these two. So it appears 5 times in this document, and 100 terms total in this document. So we got 100 terms total in this document. So term frequency is 5 over 100. Since we got 100 terms in it, we got TF defined. But what about IDF? It's the log of how many documents? 100,000 documents or 100,000 pages, which is that guy. And pediatrician is the word we are really interested in. And 1,000, we divide it by 1,000 because a total of 1,000 documents have pediatrician in them. So out of all these documents, out of all these 100,000 documents, only 1,000 have this word pediatrician. It does not matter how many times it shows up on this document, it matters how many documents have it. So we get 100,000 over 1,000, and we take the log of it, that gives me a value of 2. I multiply TF times IDF. TF was 0.05, and I multiply it by 2, I get 0.1. So this is the number that goes into the new metrics, TF times IDF. We have learned how term by term document metrics really gets transformed into this small value called 0.1. Why are we interested in doing this log of all the documents divided by all the documents that have the word of interest in it? Because it's weight of a particular word in given document in comparison to all the documents. For example, pediatrician out of 100,000 documents appears only in 1,000 documents. So I get the weight of giving me the pediatrician as a certain importance in this document. And for example, another word might have even higher importance or lower importance. So I'm assigning an importance factor to this word called pediatrician. How to create a term-by-term document matrix? First way is to do tokenization. That means breaking up into words, numbers, or symbols, etc. For example, patient blood pressure was 120, and this is another token, and that's 80. So we got how many tokens? 1, 2, 3, 3, 4, 5, 6, 7. We got 7 tokens. You know how ChatGPT charges you for the use of API? It's based on tokens. And tokens are very similarly calculated. They have their own algorithm to calculate how many tokens or the tokenization, but this is a general pattern of calculating tokens. For example, they'll charge you $1 per use of 200 tokens. How to identify tokens? One of the easy ways is to just use space as delimiter, tab as delimiter, new line as delimiter, symbols as delimiter, punctuation, dot, semicolon, colon, uh, apostrophe. So all these could be delimiters, just like we do in Excel. So we separate out these words into different columns. But not all punctuations really create tokens. That's the catch here. And so this is the Excel thing. We could do simply this in Excel, divide all the words in different tokens using different punctuation, new line, tab, space. But here's the deal that we try to do in machine learning, that we don't want 1000.50 to be separated on this dot or this dollar symbol or this comma. We don't want u.s.a to be separated out as u, s, and a as 3 different tokens. It will lose its meaning. Something we are trying to achieve with machine learning is we want to preserve the meaning of the words. Similarly, a phone number cannot be separated just based on parentheses or hyphen. So that's something we are interested in. Every token is in term by document metrics. In this is this desirable or undesirable? So the challenge here is, if every token forms a matrix, the matrix will become very, very, very infinitely huge. And we don't have that kind of computation power to process that matrix. So every token just directly does not show up into a document matrix because we don't have that kind of computation power. So what do? We reduce the number of tokens. Well, there are 5 ways to reduce the number of tokens. Conduct stemming, lemmatization, eliminate stop words, correct the misspelled tokens, identify the named entities or part of speech to reduce the number of tokens. A simple heuristic way that removes the end of words. So, for example, all these words, predictable, prediction, predict leads to a meaning called predict. Different, differential, differing, all are combined to word differ. So we created a token out of all the different kind of words, and we just generalize them as the word predict and differ. So this process is called stemming. Based on the stem of the words, we reduce the number of tokens to a single token. We got Python packages for that to achieve stemming. So based on the stem of the word, we classify all the single same stem words into just one word. And this way we reduce a lot of tokens. Another way is lemmatization. What we do here is we group the word together that have the same root or same lemma. The words might have different inflection or derivatives of the meaning, but we still group them into a single word. For example, boy, we eliminate the singular and plurals. We eliminate the past, present, and future tenses. We generalize these words. Example, be, are, was, were, been. They by themselves don't mean anything or don't add any value to the meaning of the sentence. Giving, gives, gave becomes give. Boy, boys, boys becomes boy. So we don't try to differentiate between boy, boys, apostrophe, and boys. So this way, we help the program learn better. Now, we got another strategy that we just mentioned was stop words. So, for example, tokens that have little meaning, like a, and, the, it, they, of, and, for. So we eliminate them. Simply, we eliminate these words from the learning process because they are not adding to my predictive power. They are just consuming my uh, computation power. Similarly, I try to build my own dictionary or use a dictionary previously defined in Python. Like people often tend to misspell a certain number of words. For example, they sometimes use separate with single E, sometimes with two with this A. So I bunch all those common errors together and create a correct spelling for those so that I don't create separate columns for all those words with SAPERATE being one and SAPARATE as two, and I combine them into a single word that is just the correct spelling. And this is the part of text mining. So I'm mining information from the text and clubbing them into more meaningful information. Example, fundamental with E or A becomes a fundamental with correct spelling, that is a second word. So every time person misspells them, we accept the misspelled word, but in the hindsight, text mining algorithm would correct the spelling for the sake of reducing the number of tokens. Create your own dictionary. You could simply create FL, FLA, or FLOR, sometimes misspelled, into Florida. And fall, fell, feel, fell, all are grouped into fall. Know that there's a problem with this approach that sometimes felt would mean something pertaining to the feeling. And this is the risk you're carrying by grouping all these commonly spelled or misspelled words into a single group. How do you handle this challenge? It depends on your use case, whether feeling is important for your use case. So don't put this word felt in this group because you're creating your own dictionary. So you got to be more careful and what you're trying to achieve with this machine learning or text mining algorithm. So some synonyms are grouped together. Example, slip, take a spill, found on the floor. So they all become a common word called fall. So that's the fourth way to reduce the tokens. Fifth way is part of speech tagging. So we identify the phrase like, um, and we eliminate a lot of common phrases like as well as, even if, for all that, and these three words they don't add any meaning to my machine learning. So I reduce the tokens pertaining to these words for all that. Example. Now what we are more interested in, we are interested in identifying the name of the entities. Example, University of South Florida. We don't want to split this into three tokens so that they could be treated separately. We still want United States of America to be a single token. So most common algorithms are able to take care of that, but you could modify the algorithms or create your own to achieve that. Other name entities like names, organization, countries, currencies, location, time, and percentage, these are all taken care of during tokenization because we want to preserve the meaning of those words too. Now, what the resulting table is really going to look like, the resulting table definitely will be reduced. For example, if it had like 100,000, ones, tens, 100,000 columns, like 100,000 columns, now it's going to be reduced to, for example, 80,000 columns. Is 80,000 still manageable by my computation power? Every time I'm trying to use ChatGPT, I'm using this kind of tokens. If that's the case, I really cannot handle 80,000 either. I've reduced the tokens that I'm using, but still I need to do something more about these 80,000 tokens. Problem is there are thousands and thousands of columns, and I still, even after reducing the number of tokens, I've got to reduce them even more. What do I do? All right, here's the deal. We learned that we could reduce 100,000 columns to 80,000 columns by using these techniques, including tokenization. But you know what? It does not solve the whole problem. 80,000 is still a huge number of columns, and we cannot live with these 80,000 columns because we have very limited computation power. What are we going to do about it? We've got to do something about it. We're going to do something mathematical about it. And there's an interesting technique to solve this problem. It's called SVD, or singular value decomposition. Decomposition, it's pretty obvious that you're decomposing large quantity of stuff. Here, in this case, large number of columns to smaller number of columns. You're reducing thousands of columns, 80,000, for example, in here to just maybe 300 or 400 columns or 500, 600 columns. So you're decomposing large quantity of data to just few number of columns. How do we do that? Just know that when we decompose stuff, some of the information or some of the original stuff is lost. That's why this technique is called decomposition, not like transformation. It's called decomposition. So when you decompose organic matter, what happens? The organic matter turns into like carbon, and some part is released into the atmosphere, some gets buried into the ground and becomes like uh, the soil for the future plants to grow. That's the same idea. You are decomposing tons, 80,000 columns to just 300 or 400 columns. How do we do that? Well, let me share an example with you. For example, I'm going to share a recipe database. I'll just make something up from my mind. I got a recipe. I got chicken. I got salt. I got curry, cumin. I got marination done. I got the yogurt. I heat it up for 3 hours. So time is 3 hours. And I keep processing it until it becomes tasty. What do I get? Guess what? Yes, it's called butter chicken or chicken curry. So what did I do? I converted all these data points or all these 1, 2, 3, 4, 5, 6, 7 columns to just one column, which is butter chicken. BC, butter chicken. So I converted 7 columns to just one column. And that's what this single value decomposition is. We're converting, for example, 10,000 columns to just 100 columns. The new columns, we call them as SVD or singular value decomposed columns. So this one is now part of the decomposed or SVD column. Let me share another example with you. Let's say you got the database of age, salary, and the prediction is 1 or 0. For example, we are trying to predict whether this person is a buyer of your lawnmower or not. So what do? We want to reduce, our objective is to reduce these two columns into just one column. Let's say we make something up. Our new column, obviously it's called decompose or SVD decompose column. I would still have the same number of rows. Now, in the SVD column, let's say I got 0.5 here, 0.75 in this second row, and my default prediction still remains the same, 1 and 0. So that's my target variable or the default. So how do these two data points represent this? Because I just made something up. So this is 0.75 and that's 0.5. Let me do something out of my creativity. I'll draw a line. I'll draw perpendiculars out of that. And this way, I know the distance. For example, this is 0.5. And that could be plotted as 0.75. All right. So what did I do? I was successful in translating this information into a single column by projecting this on a bisector. Well, you are right. Not all information is preserved. If I were to preserve all the information, I would have actually drawn another axis like this one and drawn the projections of this on this parallel axis to capture this data too. But I did not do that. By that I mean I did not capture 100% of the information. I might have captured like 90% though. You could still get that using these data points. But I still only captured just this. So I'm happy with 90% of information as long as it's reducing the number of columns from my original data set. What are we achieving with this? Again, objective is to preserve the data while reducing the number of features. Example, 90% of information, as long as that is preserved, I'm happy. How do I know whether how much information is still preserved? When I say preserved, like original information, new information. From the decomposed information, can I get the original information or does it capture the original information or not? That's the biggest question. I use a mathematical function called cumulative variance. As long as my cumulative variance, for example, say is limited to just 10%, by that I mean from 10% from original, I'm pretty good. I'm in good shape. I captured like 90% of the information. I can still differentiate between the data points. I could still do the clustering, or I could run the support vector machines. I could run decision trees. So I'm good. I'm going to not pay way too much unnecessary attention that I lost 10% of the information because I'm able to run all those machine learning, which again would be able to capture different patterns as long as the new data is mostly representative of the original data. So what are we doing here? First step, First step, we are translating this unstructured data. Remember that these are pages and pages of information in these rows. This unstructured data is being translated to the structured data. We translated them into like tabular columns and rows. How do we get these columns? Names and headers. We do text mining. Text mining. We did text mining. We translated them into columns and rows. And the problem is there are so many columns now in this text that I cannot really handle using my computation power. What do I do about it? I do translate these columns to SVD columns or decomposed columns, which have a reduced number. For example, these were 100,000. These are just 500. Now it's more manageable. I could run any kind of algorithm. I could run unsupervised learning. I could run decision trees. I could run random forest. I could run regression models. Whatever you say, I could run on that and learn from this data. So I could, as I just mentioned, I could run the supervised learning. I could run regression. I could run classification on the SVD data set, or I could do the unsupervised learning. We covered unsupervised learning. What it does, what it does is it creates clusters. Even if there is no target variable, it will learn from the data. And what's this data really about? It's going to tell us. It will tell us whether the data set is about technology stocks, or it's about sports, or it's about healthcare. So that's what unsupervised learning would do for us. All right, let's look at this example. There's a news story. So news story on pediatrician. How many times this was read? We have this data information, 156 times. Voters should register by, so voter related story like the politics is read by 220 times. Now we want to learn from this data what kind of stories are being read, what is more popular, and we've got hundreds of different kinds of stories and different nuances in the data set. So what do we do? How do we learn from this text related data? We are going to convert it to like a data matrix, convert that data matrix to SVD, decomposed data matrix, and we have more manageable data, maybe just few hundred lines. And we still keep the target variable the same. 156 remains 156, 220 remains 220. Only thing that changes is we have translated all this text related information to a bunch of different SVDs. So that was a regression example. It could simply now be a classification task. We could do the exact same thing. 1 remains 1, 0 remains 0, and the target variable. And we translate all this story into limited number of SVDs, which are more manageable. We could run any algorithm. We could run decision tree, which is my favorite, and random forest, which contains a lot of trees. Again, that's my favorite. So we could even do the clustering, which is also known as unsupervised learning. There is no target variable. What it's going to learn out of it, it's going to classify this as a healthcare story and that one as a politics related story. So it's going to create clusters of healthcare, politics. It will classify some of those stories as sports. How does it learn from this? It's using these numbers as a representation of this story. And there is mathematics to support what's really going on. And the observation is it does a pretty good job. Now, know that not all the times the data is labeled. The other problem is labeling the data can be difficult in real life. Most of the times, the pre-categorized data, when we have it, it would typically fall in categories, for example, like news categories, spam emails, or authorship. But a lot of times, the challenge is we don't have the data that's labeled. We don't know the target variable. How do we get the target variable? Unsupervised learning can only do so much. It's not going to be acting like your target variable developer. So some data you'll run into in your life that's not labeled. The goal, for example, in this data, we don't have the target variable, is to get the target variable a lot of times. So how do we target, how do we develop the target variable for this data? What a beautiful day. What's the mood? Let's say 1 is positive, 0 is neutral, and -1 is negative. All right. So what a beautiful day. A positive mood, that's mostly obvious. Got fired from work. This person mood could be either happy or could be sad or could be neutral. He could be happy because he was already having another job and he was trying to get rid of this job anyway. And he got like a severance pay along with it. So he could be happy or he could be sad or he could be neutral. Crying. Typically, in the case this person is unhappy, but it could also be happy because it could be tears of joy. So it's difficult without knowing the full context whether this person is happy or sad. And it requires a lot of manual effort. There's this website, Amazon Mechanical Turk, which really does this task for you. It takes a lot of manual effort. It's like a crowdsourcing marketplace that makes it easier for individual and business to outsource their process and jobs to distributed workforce who can perform these tasks virtually. Well, essentially, the task at hand is data labeling for machine learning models. There's a whole workforce that Amazon has dedicated as a crowdsourcing model available 24/7 to label the data. Because you got to read, understand, for machine to be able to follow the idea of whether this what to make out of the mood. Without knowing the context, it's not that easy and it takes human effort. Now, you need experts. One expert will prepare like a draft. Another person would also prepare another draft. Expert would combine that draft. One person to review the final data labeling solution that the two initial people have prepared. So it's a costly affair to label the data. You would need independent opinions to label the data. Example, I know this person who actually ran into this real life example at a VA hospital. His task was to classify the patient notes, whether the injuries are related to fall or they're not related to fall. The hospital wanted to know from the notes that doctors would write, called the patient notes. So they got 5,000 patient notes. Clustering algorithm won't cluster and find out which is pertaining to fall, which injuries are pertaining to accident, which injuries could be pertaining to X or Y or Z reasons. We are mostly interested in fall related reasons. How many people fell down? And how do we know that these people fell down? We need to label this data to be able to train the model so that we could predict future guys whether this person has come for a fall related reason for his injury or some other accident related reason or like a fight related reason. So there could be a number of reasons. But he was able to dedicate two experts and one adjudicator to develop these nodes for a month. Took a month to just label this data set. So two nurses and one doctor dedicated their month-long time to come up with this data set, which now has the labels, which on which now you could really do machine learning. All right, that brings me to the last slide of my presentation. What's text mining? We learn about this. It's not what Alexa would do, what Siri would do. So text mining is basically learning about the frequency, how many times this word comes into the data set, classifying them into different columns, and converting the text to manageable rows and columns. And sometimes this could be binary, sometimes this could be based on count. And this text that is mined based on frequency, based on count, is now converted to SVDs. So we are moving from unstructured to structured data set. And this way we complete our term by term document matrix, which is later converted to SVD matrix. or singular value decomposed matrix. We studied that, and once we have this SVD matrix, we could use supervised models or unsupervised models, completely up to you. And we looked at how intensive this labeling process sometimes can be using a VA project example. And we also looked at Amazon Turk website that has really dedicated a lot of resources. Even for you, you could just go, if you have a data set, just use this website to label your data set. I hope you enjoyed and you learned something from this presentation. I wish you a good rest of your day. And if you do have any job opportunities, feel free to reach out.